Hi guys, happy Thursday. And this is lesson 2 of week 2, so our second lesson of the week for science. And obviously we're looking to have a live one, but you have some tech talk today. So I'm going to post this morning, and you can tap away at it during the day. But we definitely will try some live, because that was the vote on the poll that you wanted a mix. It was generally the consensus, so we'll do that. Absolutely no problem at all. So we're going to move on, right? So I'm going to go back to the one up now. What I'm going to do, so I asked you, we had a look at obviously we've gone from, if you look at the start, we've gone from the water cycle and the carbon cycle onto climate change, and this is your homework for the last day. And I had a look at the homework folders, and most of you have that in there, so fair play, but make sure that you do get the homework in there, because I have to mark that you've engaged and you've submitted something, even an attempt. But I will correct those questions in the live lesson, so I can get some answers directly from you, so you know what everyone else is writing, and we get the optimum answers in the live lesson on Tuesday. Okay, so I'm going to go on to something new, and a couple of questions on something new as well, just to keep you just to keep us moving through the learning outcomes, because I know you've done climate change and greenhouse gases and all that kind of stuff to death, so you're well able. And this is something new, and it's in chemistry. It's in chemical reactions, it's called. And we're going to go up to the top and have a look. And this kind of touches on a load of parts of the syllabus. So it really goes into the nuts and bolts of chemistry, and what chemistry is, and how it works for elements to react together to form things like compounds and mixtures, and how we know reactions have taken place. So we're going to go through the title is Chemical Reactions. Okay, and it touches on a number of different learning outcomes, and it also touches on a number of different chapters. So I put this together before, and there's loads of what you need to know. So things like what's a chemical reaction. There's a couple of laws, the laws of conservation of mass. How do we look at the rate? Rate's a fancy name for speed. Things like activation energy, and what's a catalyst. So all those are kind of new stuff. These energy profile diagrams. How do you mess around with the speed of a reaction? I'm not even going to bother with this side here, because this side is all stuff that we're going to have to do when we get back into the lab. All these are proofs. So all these are ones when I come in and I put these up on the board and I say to you, right, here's the chemicals, here's your equipment, and off you go. So there's about 4 weeks worth of work all over on this side here, and it's all lab work, which gives us a nice few weeks as soon as we get back to the lab in February. So we're going to go this side first. That's why they're separated out. We're going to look at the difference between physical and chemical reactions. So something that's physical and something that's actually chemical. These things here, exothermic and endothermic, what does that mean? Well, we're going to find out. What is the difference between a reaction that's exothermic and a reaction that's endothermic? Things to do with collisions. I'm not talking about car crashes, I'm talking about collisions of particles on an atomic scale. We're going to look at balancing equations, and we'll get to that in a while, and then look at reaction graphs as well, and energy profile diagrams. Okay, so there's a good bit in this, and a lot of new words and so on, but we'll take it nice and slow, and then we'll try a few questions on it, and then a lot of this is not to be believed at this point. A lot of this you're going to have to look at catalysts and look at the rates and look at the difference in physical. So we're going to do all of these over here. So there's a lot, they're basically the same thing. It's just this is the theory, so you're going to have to take my word for it for now. But then when we get back to the lab, I will prove it to you over here by experimentation. Okay. So a change. A chemical reaction is a change that results in the formation of something new. So you're going to get something new when you perform a chemical reaction. So if you have something like, if you get sulfur, it's a yellow powder, I have it in the press in the back, and I get iron filings. When I heat them up, I get iron sulfide. So don't worry about remember the names, but the chemical equation for that, S is the chemical symbol for sulfur, Fe is the chemical symbol for iron, and FeS is the chemical symbol for iron sulfide. Okay, and I suppose what you're looking to have a look, if I have 3 grams, I always say to you on the board, I have 3 grams of this, take 1 gram of this, add them together, heat them up, and you're going to get something different, which is FES. Weigh that now for me, and you'll get 4 grams. To get this and this to form this, you're going to have to include heat. But the important part of this is that no change of mass occurs. So I get you to weigh 3 grams of sulfur and 1 gram of iron, you're going to get 4 grams of iron sulfide. So no change. And that brings us into the law of conservation of mass. So this definition is important. When a chemical reaction occurs, the total mass of the reactant is always equal to the products. So basically what that means up here, that if we have 3 plus 1 on this side, it's going to be equal to 4 on the other side. So it doesn't go off into the air or anything like that. You always have the same amount on both sides. If we had 6 grams, then here they have 6 grams of iron, 2 grams of sulfur. You always end up with 8 grams, and that is the law of conservation of mass. Okay. Now, if you have something like a burning candle, you've 5 grams in the burning candle, and you say to me, well, I have 3.2 grams left. Well, what's the story? Why have I not got 5 grams and 5 grams if the law of conservation of mass? Because a lot of the mass was contained in the candle has gone off. But the law of conservation of mass still stands in that if we could somehow put something over the top here and collect what is released and weigh that, that would give us 5 grams. Okay, so basically what they're saying is that the water and carbon dioxide make up the remaining mass. Okay, this also applies to physical. So chemical, remember, is if you think of the chemical, you make something new. The changing a state, you did this in first year, are examples of physical change. So if I go over here and think, okay, in first year you would have done this. Well, here's a block of ice, here's a load of water, and here's a load of gas. So this is ice, water, and steam, or water vapor. And you have arrows going between these, and you would have done states of matter. And well, if I want to go from a block of ice to water, I have melting and so on. But in this point, what we're looking at today is that if this weighs 3 grams, the water is going to weigh 3 grams, and the steam is going to weigh 3 grams. So we're not going to lose any mass. I suppose you're going to go 3 grams. You know, how do we work that out? And I suppose that's where we go by experimentation. And when we get back to the lab, we're going to be doing things like trying to evaporate water and catching it in things like a balloon, and then trying to weigh the balloon and see, does this equal this equal this? But it should be the same. So we have things like melting, freezing, condensation, evaporation. But usually physical reactions can be reversed. It's very difficult for me to go and turn iron sulfide back into them two. Very, very difficult. Because it turns into a pasty, messy stuff. Sulfur is a yellow powder. Iron is like, iron, it's like bits of grit. And when you turn it into FES, it kind of forms this sludgy stuff. Whereas if I go down here to a physical change, it's fairly simple for me to go from ice to water by melting. And then it's fairly simple for me to chuck it back in the fridge and go from water back to ice. So physical is easy to reverse. Chemical is not that easy to reverse. Okay. Onwards. Collision applies to all chemical reactions. So we'll use the formation of iron sulfide. So we have the same one as before. Iron and sulfur gives us iron sulfide. So for a chemical reaction, the particles of the iron need to collide with energy. So I'm thinking, well, if I have on my desk a bit of iron sitting there, and a bit of sulfur sitting there, well, there's just going to be a bit of iron and sulfur sitting there. So what I have to do, I have to throw in a load of energy into this. So I have to chuck a load of energy in, and usually what we do to throw energy into an experiment, we use heat energy. So we put iron and sulfur in a beaker and we heat them up, and what that causes, that causes the iron atoms and the sulfur atoms to collide with energy, causing them to move around and collide. And that's a successful collision. So if they collide with enough energy, they'll finally get to move over to our iron sulfide. If they don't get enough energy or enough heat, they will stay as iron and sulfur completely separately. So as we said there, heat causes successful and gets us our chemical reaction. Okay? And no reaction, not enough heat, no reaction. Hope that makes sense. Okay. The rate of reaction, definition, is the change in concentration per unit time. Rate is a fancy name for speed. So we're always worried about the rate of reaction, the speed of reaction. Because if it happens too slowly when you get bored and you don't want to wait and you're looking for your results and you have another class to get to and so on. If it happens too quickly, well, it could be dangerous. It could boil over. Could go on fire. So rate of reaction is always something that we're interested in. There's a couple of factors, 5 in particular, that we're going to look at. Actually more, but we're going to look at 5 that can affect the rate of reaction. And we're going to experiment using all these 5. Number 1 is the size of the particles. Size of the particles. And this is good. You're going to be sick to death looking at limestone and marble chips. The smaller the particles, the faster the reaction. Reason being is because the smaller smaller particles have a larger surface area. So if I gave you a chunk of marble and I wanted you to react it with acid, well, the acid would only have these 4 sides to attack your chunk of marble. So acid is coming in from all 4 sides. Acid and acid. Whereas if I gave you a load of tiny bits of marble, well then the acid has loads of ways to attack from all different sides and break down the marble chips and form a chemical reaction. So that's what it means there, surface area. There's more space for the acid to get in and attack your marble chips. Same, they show you diagrams here of the same idea. And that's one thing we're going to investigate. How is the rate of reaction affected by the size of the reactants, the size of the marble chips? The second one is concentration, and usually, and this is, you would do this on the same day actually, would you believe? The higher the concentration, the faster the speed of the reaction. So there's more particles present, the more likely reaction to occur. So if I go back to our example here of our big marble chip here and our loads of small marble chips here, and I'm talking about putting acid on both of these, well, as you know, I dilute the acid down for you. So I suppose I might say, right, do this full experiment with 1 molar acid and see how it affects. And you'll still get a quicker reaction down here. But what if I say, right, instead of doing 1 molar acid, do 5 molar acid. That's your second one. What you're going to happen is you're going to get a much faster experiment or faster rate down here. So there's 2 things so far. If you have the smaller the particles, the quicker the reaction. The stronger the acid, or the stronger the reactant, the quicker the reaction. Here's your second one. That all makes sense, and that's one that we're going to be doing, definitely. The third one is kind of not related. It's reactions that don't involve bond breaking are generally faster. So think if you're using ionic compounds, it's usually much quicker. Covalent is slower. So the best way to remember it is ionic is slow, Covalent is quick. The nature of the reactant. So it depends on what you're using to see whether it's going to go quick or whether it's going to go slow. This, I would say, you probably know. The warmer something is, the quicker it's going to go. So if you want to put that into words, more heat is more speed. And that's generally consistent across the way. If you heat something up and react it, it's going to happen much quicker because you're adding more energy in there. That's your fourth. Okay? For effective collisions, you need, we said this up above, you need high and you need enough energy to form a product. Best way to add in energy is heat and concentration. High concentration, high heat. High heat, if you have a lot of high heat, it means you're going to get a lot of movement, a lot of kinetic energy going, which means the particles have a better chance of forming effective collisions. Okay, not too far off now. This kind of thing, these diagrams here, energy profile, they've only put these into the course in the last couple of years. So if you start off with what you had at the beginning, you had iron and sulfur going along here. You added heat, you got over the hump, and you found iron sulfide. And that's what you have to. And this hump up here, you have to get over this hump if you want to go from reactants to products. So, bit of the lingo. All reactants must get over the hump. So they must have enough energy, enough activation energy. So this thing in the middle here, I'm just going to go in black. This here, they must have enough energy supplied to get from here over to here. If they don't, they stay at reactants, so they don't get there. So as we said before, increasing the heat. Put more energy in, get them over the hump of the, give them enough activation energy to make it over to the products. The smaller the activation energy, so the less activation energy you need, the faster their reaction. This is quite a big hump on this diagram here. The smaller the hump, the easier it is to increase the speed. Okay, so here's a nice definition for you. The activation energy is the minimum amount of energy that particles need in order to form products. So the minimum amount of energy that it needs to get from over here to here. Okay, and this is going to take, you're going to have to read through this again to go through these different points. Finally, the last one is catalysts. So catalysts, as a definition, is here. You're going to learn one definition in junior cert science, that should be it there. Speeds up a chemical reaction without being used up in the reaction. Catalysts are a chemist's best friend. Chemists are notoriously impatient, and catalysts speed everything up for you. So they speed up a reaction, and then usually you can take them back out. They don't get involved in the reaction themselves. So you don't even write them down in the formula, except over the arrow between the reactants and the products. So the reason we like them is catalysts lower the activation energy. So see what here's what it would normally look like. Now you chuck in a catalyst. A catalyst lowers the activation energy down. So if you have a look at the activation energy with the catalyst, the activation energy without the catalyst. Okay, and the great thing about catalysts is that they can be reused. You can take them out and use them again. When we do, you might remember from first year, amylase in saliva that turns starch to maltose. And we called them enzymes at the time. Catalysts are enzymes. They're just chemically produced ones. So enzymes are biological catalysts. Okay. Last little bit. A chemical reaction takes place inside living cells. So a couple of examples of chemical reactions that happen inside living cells. You have photosynthesis, the way plants make food. So just a couple of examples. You have respiration. You'll notice that this one here is the backwards version of this one here. So photosynthesis and respiration are backwards versions of themselves. And the last one is digestion, where amylase breaks down starch, as I mentioned before, starch to maltose. Okay. All right, promise last little bit. So all chemical reactions involve some change in heat. And this is important. Some give out heat, while others take in heat. And again, we have experiments to do on this. We have two types, and I mentioned them at the very start. We have exothermic reactions. If you're going to remember anything for this lesson, exothermic, heat is given out. Endothermic, heat is taken in. Good example of an endothermic reaction is when you put hand gel in your hands in the Blanch Center and you feel that cold. Good example of an exothermic reaction is when you have a fire lighting and you put your hands over and you can feel the heat given out. Exothermic, heat given out. Endothermic, heat is given in. And if you look at the energy profile diagrams for those, they will tell us two things: the size of the energy and whether the reaction is exothermic or endothermic. So in an endothermic example, the products are higher. The products are higher than the reactants. So if you have a look, so this one here now is endothermic. And in endothermic, look at the products up here and the reactants down here. Okay, so the products are higher than the reactants in an endothermic reaction. So bear in mind, endothermic, heat has to be taken in. In an exothermic one, the reactants are higher than the products. That's why when I look at one of these diagrams, I can tell straight away that this is definitely endothermic because the products are up high. This one is definitely endothermic. Over here is going to be exothermic because the products are down low. So I can tell the difference between them. And they're the same explanation, activation energy, reactant products, as we explained earlier on. Okay, this is the most common chemistry question that they've asked so far using these diagrams, and people being able to isolate whether one's exothermic, one's endothermic. This one over here is the heat taken in. This one over here is the heat given out. So if the heat's given out, the products are low. If the heat's taken in, the products are going to be high in energy because they're taken in energy. These are given out energy, so obviously the energy is going to be taken in and the energy is going to be given out in the form of heat or light. Okay, so what I'd like you to do for the rest of the class, guys, I've put a couple of questions in here for you to do. Looks a bit long, but it isn't. And then on Tuesday, what we'll do is it will give us a chance to correct the climate change ones, and it will also give us a chance to correct ones on activation energy. You might have to watch this a couple of times, it's complicated, but do your best. And any questions, you can either email me, stick a note on Schoology, or hang on to them if you want to ask them live on Tuesday. If I'm not talking to you, enjoy your tech talk, have a lovely weekend, don't be overdoing it now, take it handy, and I will speak to you next week.